Hello everyone, my name is Aditya Nair. I'm an assistant professor in the Department of Mechanical Engineering at University of Nevada, Reno. In this lecture, I'm going to be presenting a set of techniques that reduce the dimensionality of fluid flow data. So let's dive in. Now, modal decomposition methods are powerful tools in fluid dynamics. These methods help us break down complex, high-dimensional data into smaller number of modes or patterns, making it easier to analyze and understand fluid flow data. Now, the concept of modal decomposition is similar to taking a complicated piece of music and breaking it down into individual notes or chords. So in the context of fluid mechanics, these nodes might represent the distinct patterns or structures in the flow, like vortices or waves. So what is the essence of modal decomposition? Suppose you have high-dimensional snapshot data as your input, so typically that stacked matrix X that we discussed in the last lecture. We can visualize what the flow field looks like. For example, on the left is shown an instantaneous snapshot of laminar flow past a flat plate. And what you see is there is a lot of coherent structures and patterns in this data, right? But we don't know what they are. So we can visualize what the flow field looks like, the instantaneous snapshot, as well as the time averaged mean flow. So what does modal decomposition give? Now, the typical output of modal decomposition is spatial features or modes or patterns or coherent structures or instabilities of the flow. Now, these spatial features are accompanied by characteristic values, which could be either growth rates or frequencies associated with these patterns or temporal coefficients. So different modal decomposition techniques give you a different modal representation as well as different characteristic values. So each modal decomposition technique is basically classified based on typically what are the modes, what they represent, and what are the characteristic values that you can get. So here I'm showing a typical result of one of the modal decomposition techniques that we will discuss soon, where for this flow you typically observe these oscillatory structures in the flow. Now, when you look at the instantaneous snapshot, you maybe observe that, oh, there is some patterns here, but now we have a really nice, rigorous pattern that we can extract using modal decomposition for this high-dimensional flow field. All right, so the first technique that we are going to discuss is what is called as the proper orthogonal decomposition, or POD. Now, what POD does is it extracts modes that are going to capture the highest to the lowest energy content in the flow. So I'm going to try to break this down in terms of the mathematical framework. So we have our stacked matrix X, but now what we do is we first create a new stacked matrix X by subtracting the temporal mean or the time averaged flow field from this stacked data. So what I'm referring to as mathcal X here, which henceforth I'm just going to refer it as X, is subtracting the original stacked matrix X with the time averaged snapshot from your different realizations in your flow. So once you do that, you have this stacked matrix X, and what you can do is with this stacked matrix, new stacked matrix X, you can perform modal decomposition. In this case, what we're going to do is a separation of variables calculation, where you decompose X in terms of the temporal coefficients, A here, which is a function of time, and the spatial modes, phi. So you can see temporal coefficients A have time dependence, and the POD modes have spatial dependence, which I denote as psi or C. Also, we can see that the stacked data matrix, high dimensional matrix X, is a summation over n such modes and associated coefficients. just a quick recap. So what we did is we took our data, we subtracted the time averaged flow, and then we did a separation of variables to get the temporal coefficients, which are time varying, of course, and then we have the spatial modes phi here, which are only dependent on the spatial coordinates and not in time. So once we have the POD modes, what we are going to do, how do we compute the POD modes, right? Phi, that is the first question. But let's say we know how to do that. I'm going to explain that in the next slide. But if we have the POD modes, it's very easy to get the temporal coefficients. So all we need is getting to how to compute the POD modes, but once we have them, we can compute the temporal coefficients very easily. To compute the temporal coefficients, all you need to do is take an inner product of the POD mode with the stacked matrix X at every time. Now, why does this work? Well, this works because the POD modes themselves are orthogonal to each other. So because they're orthogonal and we have this nice property associated with POD modes, just taking an inner product with your entries or columns in your new stacked matrix X, we can get the temporal coefficients. So by doing this for different realizations, so x1, x2, all the way to xm, you can get an entire time history of the temporal coefficients. All right, so in the last slide, we talked about how to compute the temporal coefficients, but before that, we need to get to the spatial modes. So how do we actually compute the spatial modes for proper orthogonal decomposition? Well, there are two main techniques that are used to compute these modes. The first being what is known as the method of snapshots. So in the method of snapshots, what you do is you take this new stacked matrix X that you have, you take a transpose, you multiply it with your stacked matrix, so you take X transpose X, and then you perform a simple eigen decomposition of this matrix. And when you do the eigen decomposition, you get eigenvectors C here and eigenvalues, which is given by lambda. So you have now your eigenvectors and a diagonal matrix of eigenvalues. And from these two objects and your stacked matrix, you can actually recover the POD modes. So the POD modes is just X multiplied by C multiplied by the diagonal matrix of the eigenvectors raised to -1/2. There's a second way to compute these spatial modes for proper orthogonal decomposition, which is to use singular value decomposition of your data matrix X. So what you do is, when you do singular value decomposition, the left singular vectors are directly the POD modes of your data. So this is a comparatively much easier way of getting the proper orthogonal modes. But of course, there is a relationship between the method of snapshots approach and singular value decomposition. So the eigenvalues that you get in the method of snapshots is equivalent to the singular value squared that you get from singular value decomposition. All right, so now we know the mathematical framework behind proper orthogonal decomposition, and we can apply them to some examples. So let's first look at an example of a flow past NACA 0012 airfoil at a Reynolds number of 1000. Okay, so this is a low Reynolds number. So first, what we need to do is we need to organize the different modes by their energy content. So how do we do that? The way we do that is by just taking the ratio of the eigenvalues that we obtained from the method of snapshots approach, and the denominator is just the summation over all the eigenvalues. And we can see a sharp drop-off in the energy content of these modes on a log scale. So I'm showing you this on a log scale. The energy content of the dominant mode, which is indicated by these red symbols, is 8 orders of magnitude greater than mode 20, for that matter. I also show you, modes 1 and 2 in red, and modes 3 and 4 in red, which are, the modes 3 and 4 are shown by the green dots, essentially. And you can see that they always appear in conjugate pairs for this low Reynolds number flow. So mode 1 and mode 2 are what is known as conjugate mode pairs. Mode 3 and mode 4 are conjugate mode pairs, and so on and so forth. 5 and 6, 7 and 8, and so on and so forth. Now, looking at the temporal coefficients corresponding to these dominant modes, they show some periodic oscillations with time. Now, the temporal coefficient associated with mode 1 in red has a higher amplitude compared to that of mode 3 in green. This makes sense as mode 1 has higher energy content compared to mode 3. Now, the spatial modes themselves reveal the spatial structures of the streamwise velocity in the wake. So you can see that the spatial structures of the dominant mode are larger, which means the wavelength is larger, or the wave number is smaller, depending how you think about it. And the structures become, the wavelength of the structures become increasingly smaller for modes with smaller energy content. So this is a typical way of, for low Reynolds numbers flows that you'll see this kind of log scale, energy drop off in the modes. You'll see oscillatory behavior in the temporal coefficients, and you will see that these structures get smaller and smaller as the mode number gets higher and higher. All right, so we looked at a low Reynolds number of 1000. What happens when you go to a higher Reynolds number? So we're going to look at the same flow over a NACA 0012 airfoil at an angle of attack of 9, but now at a Reynolds number of 23,000. In fact, we're going to perform three-dimensional incompressible flow simulations over this airfoil, collect the data, and these are LES simulations, so large eddy simulations. Now you know what that means because we discussed that in the last lecture. So we performed these simulations, collected the data, and now we perform proper orthogonal decomposition on the midspan slice of this flow. Of course, we can perform POD on the entire three-dimensional data. It's computationally challenging, but it can be done. Now we again organize the different modes by their energy content. This time, we don't see a sharp drop-off in the energy content of the modes. In fact, the energy content of the dominant mode is only 5 times that of mode 20. Now this tells us that the energy content in the higher Reynolds number flows are distributed among multiple modes. Now the temporal coefficients associated with these POD modes, you can see that they don't evolve in this nice, regular, oscillatory, periodic manner. There's a lot of different types of oscillations that are happening of these POD modes. And again, I want to point out that the red stands for the dominant mode, which is mode 1 and mode 2, and the green stands for the second dominant mode pair, which is 3 and 4. Now, the modes, the spatial modes, again, revealing the structures of the streamwise velocity in the wake, you can see mode 3 has actually larger spatial structures than mode 1. So that intuition of this kind of, higher mode numbers have smaller structures doesn't hold. And this is particularly because now this flow that we analyzed has turbulent behavior. So when we look at this flow, the energy content is distributed among a lot of different modes. So that N that we talked about, the summation of the modes that described our stack matrix X, we actually need a lot of them to be able to accurately reconstruct the original flow. Well, we don't need a lot of that in the low Reynolds number case, but definitely for this higher Reynolds number case, we need a lot of modes to accurately represent the full data, matrix X. So hopefully this gave you an intuition of the differences between a lower Reynolds number POD versus a higher Reynolds number POD analysis, and the different flavors. So now you have some intuition of what that brings about. All right. So now that we have already looked at and discussed proper orthogonal decomposition, let's look at another technique for modal decomposition. So the first question that you will ask me is, well, why is there a need for another technique, right? So in POD, the modes were organized by energy content. But that doesn't mean that these modes are the most dynamically important modes of your system. Now that's where modal decomposition in the form of dynamic mode decomposition comes in. Before we dive into dynamic decomposition and the method itself, I've just wanted to discuss how, again, to organize the data for performing DMD. The matrix X is again arranged, the columns represent time realizations, and the rows represent the different spatial points, as well as the variables, as you will know, because we discussed in the last lecture. So in dynamic mode decomposition, we also create this new matrix, which we call as X prime. And X prime is just a shifted matrix X by one column, which means you can see that the first column of X prime is X1, whereas the first column of X is X0, the second column of X prime is X2, and the second column of X is X1, and so on and so forth. Now, what is really important in DMD is that each column of X has a shifted column in X prime that is shifted by a particular sampling time, right? So it is not necessary to have the same sampling time across each column in X and each column in X prime, as long as the associated columns in both X and X prime have the same fixed sampling time step. We also note that there is no need to subtract the time averaged mean for performing DMD. So once the data matrices are organized, what does DMD give us? DMD gives us a really nice linear relationship between X prime and X, this time shifted X and X. How do we get this A? Well, we can perform a simple regression operation, linear regression operation, to get A. However, the issue with this is this might result in an ill-conditioned A, which is not great. And for fluid flows, especially for these high-dimensional fluid flows, it's really important to perform this analysis correctly to get the accurate, dynamically important modes. All right, so if we don't perform regression, how do we go about getting this A? And how do we get the DMD modes, right? That's what we are after, is these modes along with these characteristic values, right? We're not interested in the operator A, but this low dimensional representation, which are these dynamically important modes in the flow. So to perform DMD, we typically start with performing singular value decomposition of our data matrix X. Now, this is similar to what we did in proper orthogonal decomposition, where we just perform singular value decomposition, and the left singular vectors essentially were just our POD modes. Now, in the case of DMD, we do not need to perform a full SVD of our data matrix. In fact, what we do is we truncate the rank onto the first R POD modes. So we do this, singular value decomposition, get phi, sigma, which is your singular values, and get, your right singular vectors C, okay, but in a rank truncated manner. All right. Then what we do is we construct an approximate operator A tilde. Now, the main intuition behind the approximate operator, and this is the main idea behind why dynamic mode decomposition is so popular in fluid dynamics as a dimensionality reduction technique is to express is that the approximate operator A tilde is a projection of the linear operator A onto POD modes. That's it. So when we just perform SVD, we got POD modes. If we just project the operator A onto these POD modes, what essentially comes about is this approximate operator A. And it makes for a very tractable way to get these dynamic or these dynamically important modes in the flow. So now we just do two substitutions. We substitute the fact that A tilde is just U transpose AU. U here just stands for phi, which is the left singular vectors. And we substitute that in x prime is equal to AX, as well as the rank truncated SVD decomposition that we had in the first step. And when we do both of these, we get a really nice representation for what A tilde is. A tilde is nothing but phi r transpose multiplied by x prime multiplied by the singular vectors, the right singular vectors, CR multiplied by the singular values raised to -1. So now that we've got what the approximate linear dynamics of the system is, we can perform eigen decomposition of this A tilde operator to get mu j and tilde Vj. So the eigenvalues are mu j and tilde Vj is the eigenvectors of this approximate operator A. Now you'll ask the question, okay, we got the approximate operator, but what is the true DMD modes, right, of the system? Well, that's actually easy once you get the approximate operator. It is a simple, because A tilde and A have this beautiful relationship between each other, we can use the eigenvalues and eigenvectors that we got from the approximate operator A to construct the true DMD modes. So you can see here V actually is, or VIs are the DMD modes of the true linear dynamics of the data that we'll get, and lambda j is essentially the eigenvalues associated with the linear operator A. And I must note here, delta t is just the sampling time step that we had discussed before between this x prime and x. So now you can see that, for performing DMD, a quick recap, what we do is we do singular value decomposition. We use the idea that A tilde has a relationship with A through these projection onto POD modes. And then by substituting this fact onto this x prime is equal to AX equation, we get a nice looking expression for A tilde. And then we get the eigenvalues and eigenvectors from that. And from the eigenvalues and eigenvectors, we can now recover the true DMD modes, which is Vi in this case, and lambda j, which is the eigenvalues associated with these DMD modes. Now, I must note that these eigenvalues or these characteristic values that we get associated with the DMD modes represent the growth rates and the frequencies of the system. So usually what you'll end up getting is each DMD mode, which is usually complex valued, and I'll get to that in a bit, is each mode has this kind of complex representation. The complex only stands for some kind of phase relationship between these modes. So these modes are exactly the same but offset with a phase. And the eigenvalues that you usually get are, again, you get a real part and an imaginary part. The real part usually stands for the growth rate, and the imaginary part usually stands for frequencies or these oscillatory frequencies associated with the dynamic modes. Now, I want to again make a quick note before we move on to examples, is that when I say that these DMD modes are associated with the frequency, each DMD mode only oscillates at one frequency. So this is, different from the proper orthogonal decomposition that we discussed, before, where for the low Reynolds number, we saw that we get these oscillatory modes with a single frequency. But for the higher Reynolds number, we saw that the POD modes essentially had this complicated temporal dynamics. That's not going to happen in DMD because each mode has, or the temporal coefficients have a particular frequency, so they evolve in an oscillatory manner only. All right, so now that we understand, what is DMD, how to perform DMD, let's look at the same two data sets that we looked at before, the POD analysis, right? So now we're going to do DMD on this flow over a NACA 0012 airfoil at low Reynolds number at alpha is equal to 9 degrees. I want to note that this is incompressible flow. So first, just like we had organized the structures by their energy content in the POD modes, we can organize them by their dynamic importance in DMD. So how do we actually quantify the dynamic importance? Now, this is a very simple operation that you can perform. You can take the eigenvectors or the DMD modes, the V's that we obtained, and then multiply them with one realization of the flow. Now, I'm going to choose this realization to be the initial snapshot in the stacked data matrix X, which is X0. Now, when you organize them, this gives us the relative importance of the modes, just like what we got the energy content in terms of POD. So we organize these modes based on this metric B, which gives a relative importance, and it reduces from the most dominant modes to the most to the modes of lower dynamic importance. And I want to note here that we didn't subtract the mean of the flow when doing the DMD analysis. So because we didn't subtract the mean flow or the time average flow is going to be the most important mode in this DMD analysis. So you can see by the blue dot, which is essentially just the time averaged mean flow, that has the most dynamic importance, followed by these red dots, again appearing in these conjugate mode pairs, and the green dots, which have this kind of relatively more dominance compared to the other modes of the flow. And you can even see the same structure on a log scale in terms of the mode number 20 has very little dynamic importance compared to this to the red and the green modes, essentially, right? So now we looked at relative importance, but we also want to look at characteristic values. Now, this is similar to the temporal coefficients that we obtained in the POD modes. Now, in the DMD modes, we get some growth rates and frequencies associated with the DMD modes. So what I'm showing here is a plot of mu, which is the eigenvalue associated with the approximate operator, A tilde, which will lie on a unit circle for the nonlinear modes, nonlinear flow. So why is it on a unit circle and why not outside and inside? Now, in the case of linearized flow, where the modes can actually grow or decay, the values will lie outside the unit circle if it grows and inside the unit circle if it decays. We can see that the blue eigenvalue, which is corresponding to the time averaged flow, has a real part of 1 and an imaginary part of 0. And this is because it has no frequency associated with it, because it's a time averaged mean flow, right? Because it's a mean flow, it has no oscillations. And we see that the other modes occupy other values on this unit circle. And for 20 modes, this is pretty well spread out. Now, the DMD modes, mode shapes that we get for mode 1 and mode 3, so this is for the red and the green that I'm showing you, they look very, very similar to what we obtained from POD analysis. So this makes sense if you think about it, because DMD modes are oscillatory in nature and they have associated frequencies. Now, the POD modes that we obtained by organizing them on energy content were also oscillatory in nature. So you're actually going to get pretty much the same dominance in energy spectra when you look at this low Reynolds number flow. So we are actually seeing pretty much the exact same spatial or modal structure for the DMD mode as we had in the POD mode. So one consequence of this is, in cases of low Reynolds number flows, the most energetic modes and the most dominant modes are similar. All right, so now look at what happens when we perform DMD on the higher Reynolds number flow. So just like before, we are going to quantify the relative importance of the modes, which is B. Now, the mean mode has the highest importance that we see, but just like in the POD modes, the dynamic importance between the other modes is spread out, right? You can't really make out this really nice log scaling between these modes. They pretty much have similar dynamic importance in some sense. Now, looking at the eigenvalues, though they all lie on a unit circle because this is nonlinear flow, we see that the eigenvalues are much closer to the mean flow and less distinctly spread out, as was the case with the lower Reynolds number flow. We also see that the mode shapes are completely different now, right, than what we have seen before. So we see we have seen these structures in POD as well, but for mode 1, I would say the structures are similar, but mode 3, the structures are kind of completely different to what we observed in the POD decomposition. So in some sense, what DMD offers is this notion of dynamic importance of the modes as opposed to energy content. And the punchline is that, these modes, if you were to, predict the flow or reconstruct the flow, it is very important that you include these modes in your reconstruction for representing your underlying flow behavior. All right. So we talked about proper orthogonal decomposition and dynamic mode decomposition in the last slides. Now, POD captures the spatial coherent structures, while the DMD modes represent, essentially a random realization of the coherent structures. So the question becomes, can we combine the advantages of POD and DMD? The answer is yes. We can do what is known now in literature as the spectral proper orthogonal decomposition. Now, the spectral proper orthogonal modes are optimally averaged DMD modes, essentially, and they describe best the statistical variability of the coherent structures in unsteady fluid flows. Now, one feature for the mathematical enthusiasts is these modes are orthogonal under the space-time inner product, as opposed to in POD, where the modes in POD were orthogonal from a space-only inner product. So these SPOD modes, or the spectral proper orthogonal decomposed modes, vary both in space and time. All right, so we talked about, SPOD being this kind of nice middle ground between DMD and POD. How do we perform it? So for performing SPOD, what we do is we chop up the data into NB blocks, and then we perform discrete Fourier transform on each block. So you can see that for block 1, 2, up to NB, we perform DFT and we get this X hat representations, right? So the X hat variables contain the Fourier component or at frequency, say Fk, in each of the nth block. Now, then what we do is we take all of these individual, components of each block, and then we use that to solve an eigenvalue problem. Okay, so you can see that we compile this, this matrix X hat Fk, which is essentially all the columns of these different blocks. We assemble them together, we do X transpose, and we do an eigen decomposition of X transpose. Okay. Now, we can of course perform this operation to get the SPOD modes. The SPOD modes here is psi, and the characteristic values of eigenvalues associated is given in this lambda matrix, but they all represent a particular frequency of the mode, which is what DMT was giving us, but also this, this nice way of chopping the data up and doing, this X transpose X or XX transpose eigen decomposition also gives us something in terms of energy content associated with a particular frequency. Right? So algorithmically, to implement this eigen decomposition, there's a simpler way, and I urge you to look at the papers and the code that is tagged on your slide to play around with this. But what we get out of it is these optimally averaged DMD modes of the flow. Right? You'll see, just a note, is in this eigen decomposition, there is also this weight matrix W. Now, what this weight matrix does, it avoids any spectral leakage in the windows because you're chopping up this data into blocks. So the W avoids that. And it also stores the value for doing numerical quadrature, for example. All right. So now we looked at three modal decomposition methods, which is POD, we looked at DMD, and then we looked at SPOD. Now, what we're going to look at is, something called as extended dynamic mode decomposition. Now, why is this needed? To get a more accurate representation of the nonlinear dynamics, one can perform regression on an augmented space. Okay, so an augmented vector that contains nonlinear measurements of the state instead of directly performing the regression on the state itself. And you can think about this as, this augmented state encodes kind of more information, and regressing this augmented state gives you more details on the evolution of these states of the flow. Because as we can imagine, these states or these high-dimensional states are coming by solving these, complex PDEs and conservation laws that we discussed in the last lecture. So, getting all of this represented in a linear dynamical sense is a hard task. So one way to, get it more accurate is by augmenting the state. All right. So we can augment the state by phi, essentially, and you can build this, enriched state representation. Now, what does this enriched state do? It provides a basis to approximate what is known in literature as the Koopman operator. So Koopman in 1931, that's a long time ago, but he demonstrated that it is possible to represent a nonlinear dynamical system in terms of an infinite dimensional linear operator acting on a particular space of measurement functions of the state of the system. So the question becomes, what are the measurement states of the function? If we can get an answer to that, we can get the Koopman operator, and the Koopman operator being, an infinite dimensional linear operator can give us a lot more idea about this kind of flow evolution. So it embeds all the nonlinearities into this infinite dimensional Koopman operator. Now, I must say that, we talk about infinite dimensional Koopman operator, but in practice, we always will have a finite dimensional approximation of this Koopman operator. Now, one way of doing this is by doing extended dynamic mode decomposition. In extended dynamic mode decomposition, what you do is you again perform this regression, but now on the augmented space. Now, in practice, just doing the regression on the augmented space is computationally expensive. So what you do is you use kernel methods. So this is using kernel methods. I'm just illustrating constructing G and A, and when you basically do G with a pseudo inverse of G multiplied by A, you get an approximation of the Koopman operator. So once we get the Koopman operator, all the other steps follow. We can perform eigen decomposition, and we can get the Koopman modes phi here, right? All right. Before we discuss an application of the extended dynamic mode decomposition, let's do a quick detour and almost a 2-slide crash course on neural networks. So In this age of data science and machine learning, I'm sure you must have heard about neural networks. But we need to first understand what is the fundamental building block of the neural network. Now, this is the Rosenblatt's perceptron. Functionally, if you can think of a neuron, right, in your brain that transmits information, processes that information through synaptic connections, the perceptron is an artificial neural network that is based on a similar idea. And the main purpose of the perceptron is to classify patterns in your data, right? Now, you can see that this network consists of nodes, each with its own input. So x1, x2, x up to xn. So each input, and these are all nodes. And summing the nodes essentially of this neural network computes a linear combination of the inputs. And these linear combinations are, and you can apply an external bias to this linear combination that you get, right? Now, the resulting sum is called as an induced local field. Now, what you can do is you can take this induced local field and apply what is called as a hard limiter to it, which is denoted by the symbol phi. Okay, so what happens when you perform this hard limiter is if the neuron produces an output, the neuron produces an output equal to +1 if the input is to the hard limiter is positive, and the output is -1 if the input again is to this hard limiter is negative. Okay, so you can think of it as any negative variable that gets summed up. You pass it through this hard limiter, and it gives you a -1 index. And when it's a positive value, it just passes again through this hard limiter, and it gives you a +1. Now you can kind of visualize why this is so useful, because if you can have this kind of binary classification into +1 and -1, then you can classify patterns in your data, right? So typically what is done is the weights of this neural network are updated on some learning algorithms, right? So you can see this W1 to WM, they're all updated based on some learning algorithms. Now, I must note that this perceptron is only limited to classification of linearly separable patterns in the input data, right? So if there are nonlinear patterns that you want to extract or some relationships, it is not possible to do so. So this led to the development of what is known as the multi-layer perceptron, right? Which includes nonlinear activation functions that are differentiable. It also includes multiple hidden layers and a high degree of connectivity between the artificial neurons that are determined by synaptic weights, right? So there are two main phases for training the multi-layer perceptron. In the forward phase, the weights are fixed. The input signal on the left, so this x1 to xm, is propagated, right? And they're propagated through the network layer by layer until it reaches the output, right? Now the activation functions and the outputs are modified in this step in this forward phase step, right? In the backward phase, what happens is an error signal is produced comparing the output of the network and the desired response. So you essentially provided it that, oh, my neural network should give me this desired response. I compare what the current output is with the desired output, and that produces an error signal. And this error signal is basically propagated backwards, and the weights of the network are updated. Usually these algorithms for updating the weights are called as back propagation algorithms, right? So you can see that there is an input layer, there's an output layer, and there is a lot of layers in between. These layers in between are what is known as hidden layers. The role of the hidden layers is to perform a nonlinear transformation of your input data, just like what we saw in eDMD, but with more complex activation functions and synaptic weights. All right. So now we get to the meat of why neural networks are so popular, right? The reason why neural networks are so popular and powerful is because of this concept called as the universal approximation theorem. So there is this particular class of neural networks called as recurrent neural networks, where the connection between the nodes can create a cycle. So allowing for outputs of some nodes to subsequently affect the inputs of the same nodes. Now this allows us to embed essentially a complex temporal pattern in our neural network dynamics, right? Now the leftmost item of the figure that I show, there is a recurrent connection which is given by V, and I show an unfolded representation of this in time, and you can see that this unfolded representation produces a bunch of different layers. So you can think of this as layers embedded within a particular neuron itself, right? Now, of course, there are multiple neurons in a multi-layer perceptron that are connected to other neurons, but if you do this recurrent connection, you're creating essentially more and more layers because the outputs essentially affect the input, right? So there is this nice recurrence property that you can take advantage of. So this leads us to the universal approximation theorem, right? Which says that any nonlinear dynamical system may be approximated by a neural network to any desired degree of accuracy with no restrictions imposed on the compactness of the state space, provided that the network is equipped with an adequate number of hidden neurons, right? So that's a lot to unpack, but essentially what it says is, hey, you can approximate any nonlinear dynamical system just by using a recurrent neural network. Now the key here is an adequate number of hidden neurons, right? So that is where all of the, you must have heard hyperparameter training and all of these concepts comes in. So the fundamental concept behind neural networks are the ability of these hidden neurons to perform nonlinear transformations of your input data. So we talked about augmenting the space to perform nonlinear transformations. You can imagine a lot of these hidden neurons through these activation functions are essentially performing these nonlinear transformations. So by training, the synaptic weights along with the activation power functions, you get a really powerful machine, right? So the universal approximation theorem is pretty powerful. So mathematically, how we write this is as a state of the system in the n+1th layer is obtained from the weights and biases applied to the previous layer passed through an activation function. Generally, this activation function is a nonlinear function. So a tan H function, you'll see that appearing a lot in the neural network literature because it provides a really nice nonlinear transformation of the weighted sum that you get at each node. So think about the activation function, which in the last time when we discussed this, phi function, which was the hard limiter. In the multi-layer perceptron, we talked about phi being an activation function, and now the phi, we have a form of it, which is this explicitly tan H form, which performs a nonlinear transformation of your data, essentially. All right, so why did we take this quick detour, right? Is we can actually now use neural networks to actually augment our states, right? So the phi that we had discussed before, I told you that what are the measurement functions, or Koopman said, if we can figure out what these functions are, then that would be great. That then we can really nicely construct this infinite dimensional Koopman operator, right? So what we're going to do is we're going to augment this space by a simple 3-layer neural network. Essentially, the exact same concepts that I talked to you about in the last slide is you have all of these weights, and for the last layer, with the last biases, you have your augmented vector phi for your input vector x is just through this kind of nice 3-layer neural network. Right? So at the end, you're going to get these phis that you got, and you're going to augment them, and then you're going to build this eDMD machinery out of that, right? So we can perform this on a Kuramoto Shivasinsky PDE, and essentially what I'm showing here is on the left is just the exact evolution of this PDE, right, in time. So the y-axis is time, the z-axis is the variable or the PDE variable. You could think of this as being velocity. So there is some propagation of this velocity in time, and that's the exact construction. So along with this kind of feed-forward neural network construction, which is shown in the second column, we can also compare it with other augmentations, not based on neural networks, right? One is we can use the state and its spatial derivatives. And the other one is we can use the state and its Fourier coefficients, right? To basically build an enlarged basis representation, regress the dynamics, and then look at this evolution of the PDE. And what we see is, clearly the eDMD DL, which is this neural network-based DMD, kind of outperforms both the other approaches. In fact, the other techniques don't pick up the fine scale structures of the solution, and the eDMD with the neural network does. All right, so we did a sort of a crash course in neural networks in the previous slide. So now you're going to see an application of neural networks to compress the fluid flow data. In particular, we're going to look at autoencoders. Now remember the hidden neurons of the multi-layer perceptron trained with these forward phases and backward phase, which was the backward propagation algorithm, plays a critical role as feature detectors, right? So we took this data that we have, we can perform some nonlinear transformation using activation functions, and this nonlinear transformation helps us in feature detection, identifying these niche nonlinear features of the problem. So this feature detecting property of the multi-layer perceptron can be exploited in its use as replicator or identity maps. So what I mean is we want to produce the same input signal X at the output layer. So this is nothing but an identity reconstruction problem. Is you have an input layer, you pass it through the neural net machinery, and at the output you basically get the same signal as the inputs, right? So if we use POD to perform this identity map, that is equivalent to actually doing a linear neural network. Okay, so what does a linear neural network mean? A linear neural network is a network with linear activation functions. So there are no non-linear activation functions in this neural network. So if you just perform your standard SVD of your data, the singular vectors associated with the singular values provide you with a compressed representation of your data. So a natural question to ask is, what if you use nonlinear activation functions, right, to train your neural networks? In addition to having this nonlinear activation functions, we can also impose a special structure to the design of the multi-layer perceptron. Now, in the special structure, you essentially pass the input layer through a bunch of different layers till you reach a hidden layer with a smallest set of perceptrons. Now this hidden layer with the smallest set is called as a latent space, right? So this in effect, when you train this with data, this fully trained multi-layer perceptron essentially performs the role of an encoder. So it encodes this high-dimensional dynamics X into this small latent space vector Z. Now, to reconstruct the estimate of the original input pattern X, we can apply the encoded signal in Z to another hidden network, essentially called as the replicator network. In effect, this latter network basically performs the work of a decoder. So you can take this compressed representation and then decode it into the full high-dimensional input representation that you had before, right? So in the figure there, phi is the encoder and psi is the decoder, x is the input, and x hat is your output estimate, which essentially has to be the same as the input estimate, which is x. right? So the smaller we can make the size of the hidden layer or this latent space, the more effective the compression is, right? So this gives us a really nice, use case of applying, multi-layer perceptrons to this identity reconstruction problem. So from a mathematical point of view, what you're doing is you're trying to minimize the error between the estimate, which is x hat, and your encoder decoder. So first you apply the encoder, which is phi x of m, and then you apply the decoder, which is psi of phi of x of m, and you're trying to minimize this error. And if you can do this really well with the most compressed representation of z as possible, then you have essentially discovered an inherent low dimensional structure of the data, right? So so essentially what this means is we can take high dimensional flow field input that comes from, say, a cylinder flow simulation, direct numerical simulation at a low Reynolds number of 100. We can then encode the snapshots inputs using a particular perceptron architecture. In this work, CNNs are used to get the latent vector R. Okay, so you're going to get this latent space representation or latent vectors R, which is this hidden neural network of just consisting of two perceptrons. In this case, we can compress it to just these two latent space variables, which is R1 and R2. So then what we can do is we can take this individual latent space coordinates, or these compressed coordinates, and then decode the individual latent space representations to get high dimensional representations of the flow. So you take R1 and R2 here and decode the information individually, again through some hidden layers, and get Q1 and Q2. And then what you can do is you can add Q1 and Q2 and reproduce the output. So this identity map, right? So your input was Q, now your output is this estimate of Q, and you want both of them to be the same with the least error between them, right? So so basically, what is done in an autoencoder is this identity reconstruction problem, but the nice thing about this is you can take the data, you can decide what your latent space dimension is, decode the individual latent variables, and then combine them to form the output. You can see this in action in the results for cylinder flow. So the reference on the left is direct numerical simulation snapshot that is shown. And we also show the reconstructed flow field from applying proper orthogonal decomposition, right? So you can see that we talked about proper orthogonal decomposition being equivalent to constructing using a linear neural network, and you can see that clearly in the third column. You have this linear network without any nonlinear activation functions, and essentially they produce kind of the same flow field with very similar L2 errors, right? And the moment you introduce this nonlinear activation function, which is tan H, which encodes and performs this nonlinear transformation of the data, you can see that the error is reduced a lot. So you can see that by compressing this data, this high dimensional data using autoencoders, you can meaningfully represent the states of the flow. Right. So now the question becomes, is there a relationship between what you get with the compressed representation using this nonlinear activated neural network versus POD? Well, what you actually see is when you do a POD analysis of these decomposed fields Q1 and Q2, the Q1 is nothing but a summation of POD modes, spatial modes 1, 2, and 3, 1, 3, and 5, and Q2 is a summation of spatial modes 2, 4, and 6. So essentially what the autoencoder has figured out through training and backpropagation and minimizing this error is, hey, I need to encode these kind of alternate POD modes and sum them up and represent them as Q1, and then some maybe the POD 2, 4, and 6 and represent them as Q2. And in fact, all of this is coming from this simple latent space coordinate, again, which embeds all of the singular values associated with POD mode 1, 2, 1, 3, and 5, and 2, 4, and 6 respectively, right? So in some sense, it provides an extremely valuable compressed representation of the system dynamics. All right, so we talked about POD, then we talked about DMD, then we went on a journey to discuss extended dynamic mode decomposition using neural networks. Then we discussed about autoencoders and their value in this identity reconstruction problem. Now we're going to look at non-classical and non-traditional dimensionality reduction techniques. So in this first method of these non-traditional ones, I'm going to discuss what is called as network community-based reduction. So essentially, for this, we first need to define what the network representation of the fluid flow is. So a network typically consists of nodes and edges, and each of these edges have weights. So in the neural network, we had to train the weights of the system. But if we know something about the interactions in the system, so we have some domain knowledge, we can actually impose the edge weights between the nodes to actually create the network. So for a fluid flow, we typically have vorticity data at each grid point, say from a computational simulation or from doing PIV. So in this network, we are going to use the vortex strength or the vorticity at a particular grid point as a numerator, and the distance between the vortices as the denominator, essentially. Simple enough, right? So you have the vortex strength. So if I have some vortices in the system and they are interacting with one another, if I am an influential vortex or I have a greater strength, I have more influence over the other people around me. If I'm closer to the other vortices, I have again more influence with the people that are closer to me, right? That's what this network representation means, right? So now once we have this network representation, we can use tools from network science. One of the most popular tools in network science to extract something called as community structure is the modularity maximization algorithm. So what this algorithm does is it partitions your data into optimal communities or partitions, essentially. So you can see this network of 9 nodes has the single edge between 2 of the nodes. And what it has done is it has taken all of the other nodes as being the communities, and it has separated out these 2 communities from each other, which is the blue and the orange, right? So the community detection is some kind of way of assigning memberships to nodes in your network. And that is exactly what we do for fluid flow problems, right? So for a flow past a cylinder and a flow past an airfoil, we can take the full high dimensional flow field. We can, we already know what from direct numerical simulation or performing PIV, what is the vorticity at each of these points. We know where the grids are placed, so we know the distance. We can compute this adjacency matrix A. And we can feed this adjacency matrix through this modularity maximization algorithm to get membership groups or this community structure. And what we see is the nice thing about this is that all of the vertical structures in the wake have their own membership classes, which I want to point out that this is not a vortex identification method, but in some sense, it identifies some kind of structures in the wake of these problems, right? Now we can go one step further and we can take each community membership and take the centroid of those community memberships and use them as nodes of the system to create reduced representations of interactions, right? So now you can envision the graph in the bottom is where now you have these, different nodes, in your full high dimensional flow field. So you only have 7 nodes essentially that have these kind of relationships with each other. So you can get a really nice reduced representational system, and you can use this representation, for example, to predict the lift forces of the body or to predict the deflection of structures of the body. So in essence, this is a non-traditional tool to provide you some dimensionality reduction using tools from network science. All right. So in the previous slide, we talked about network-based representations for high-dimensional flow physics, but usually you may not have access to all the high-dimensional flow field. What if you have access only to the low-dimensional observables or measurements, right, or output observables? How then do we go about constructing the network, right? So what you can do is you can perform unsupervised centroid-based clustering of the phase space of the system. So which means if you have these output observations, which is y, you can figure out the centroids in your measurement space that minimize the inter-cluster variance between in your data, basically, right? So if you have your data and I want to figure out the centroids in this data that have the least inter-cluster variance, right? So so you can see here is the the measurements y. You can identify these centroids now, just like I talked about community-based centroids. These are centroids just based on this cluster data, right? So it basically provides you a way of giving cluster memberships to each data point in your measurement space. So suppose you have some time history of lift coefficient, drag coefficient, and say the time derivative of the lift coefficient. What you can do is you can do this unsupervised centroid-based clustering and identify these 10 different clusters, right? And once we have these 10 different clusters, what we can do is we can identify the centroids of these clusters. Now, each point on this, on the trajectory or the time history of these measurements have their associated high dimensional flow field, X, right? So what you can do is you can average all of the high dimensional flow physics within a particular cluster to create a centroid based high dimensional representation of what your cluster is, right? So on the bottom, I show you these, clusters, high dimensional cluster states of the system. Now we can go one step further, and because we have these trajectories clustered, we can see when does a particular trajectory go from one cluster to the next cluster. In fact, this is identifying transitions between the clusters. And just by a simple box counting way, we can actually compute the probability that, say, the trajectory would go from cluster 1 to cluster 2. Now, I want to give you an intuition about the cluster states. If you just had a periodic signal and you do this clustering, what you will get is this the states being chopped up into different phases. So if you had 10 clusters, you would have chopped up the entire periodic signal into 10 different phases, essentially, right? And you could do the same exercise. Now, in here, I'm talking about turbulent flow past an NACA airfoil. So of course, some of the trajectories are not periodic. So you can then, nicely organize what are these cluster transitions, right? So even in the cluster transitions, now that you can count, what is the probability of the state transitioning from, say, cluster 1 to cluster 2 and cluster 2 to cluster 3, you can assign this in a network way, right? You can visualize this in a network way, right? So you can see on the bottom, I'm just showing you, the network, the cluster-based network of this. So you have these 10 different clusters or these centroids and these 10 different high-dimensional states. And what you actually see is the thickness of the line indicates how likely it is actually to go from this particular cluster to the other cluster, right? And the nice thing about, this network formulation, it can identify, if I need to reach, say, example, states 9 and 10, which clusters do I actually need to go through, right? So in this example, I need to go through cluster number 7 or cluster number 8, or cluster number 6 and cluster 6, 7, and 8, essentially to go to cluster 9 and 10. Right? This is not obvious by just looking at the clustering plot of the cluster states. So this cluster transitions gives you some kind of map of organization of your data, where this data was and where it is going. right? So this is like, you must have heard about Markov chain. This is just an example of constructing a Markov chain model from your data, essentially. All right, so quick recap on what we covered in this lecture. We talked about different modal decomposition techniques in fluid flows. We did a small introduction on neural networks, and we introduced some, non-traditional, dimensionality reduction techniques as well. Next up, we will talk about methods for building reduced order models for fluid flows. See you there.